Hi, I'm Mitchell. In this talk, I'll describe how we're aligning machine learning performance metrics with the reality of users' experience. Moderators, researchers, and engineers want classifiers for critical social computing tasks that they can easily deploy at scale. Tasks like toxicity detection or misinformation detection and enforcing many other community-specific norms. Taking toxicity as an example, it would appear we're in luck. For instance, in this popular toxicity detection task on Kaggle, models achieved up to 0.95 ROC AUC. And these high scores can make people feel pretty safe about using these classifiers in their systems. In this talk, we're going to demonstrate that 0.95 ROC AUC score is inflated, as are many scores in social computing tasks. We're going to show you that this specific score should actually be closer to 0.73, a much less convincing number. So what's going on here? Well, let's start with an observation. Unlike traditional ML tasks, even experts often disagree on the correct labels for tasks in social computing and HCI. For instance, we expect everyone to agree that this is a dog. But while this comment contains some clearly objectionable material, in the expert labeled datasets that we looked at, not every expert felt this comment crosses the line. It was basically a split jury. And this means that the traditional approach of evaluating ML models by aggregating annotations to reduce noise breaks because it flattens out disagreement from test sets. So in this example, a classifier could predict toxic and receive a perfect score because it matches the test label, but 2/5 of annotators might disagree. So scores become artificially inflated above the user experience. In this work, we ask, can we transform existing ML metrics to better handle disagreement? To try to do this, we introduce the disagreement deconvolution. So as I mentioned earlier, there's lots of disagreement. For tasks ranging from toxicity detection to Reddit moderation, somewhere in the range of 1/3 of annotators disagree when content is labeled as problematic. And this disagreement isn't necessarily wrong or bad. Tasks in social computing and HCI often attempt to categorize the messy realities of our lives, and we don't want to drown out the viewpoints that people hold. But it does place fundamental limits on how well any classifier can perform when deployed, because in practice, these classifiers often require a single decision. Do I remove this comment or not? And no matter what decision we make, people are bound to disagree. We think that at the very least, we should compare predictions to each annotator's belief, essentially inserting one label per annotator into the test set. So in this case, now if a classifier predicts toxic, it would receive a score of 0.6. But here's the problem. Some of those annotations might be noise. In these crowdsourced datasets, people worry that labels might be clicked accidentally, or someone might have momentarily misunderstood or not paid enough attention. So we can't just take the labels as is. How can we cut through that noise? Well, imagine a world where we could ask the same person the same question multiple times. If we could do that, then we could find what we propose to call an annotator's primary label, or the label they'd say most often. In our work, to help reduce annotator noise, we propose creating test sets consisting of each annotator's primary label. And it turns out, this world is not entirely imaginary. Many crowdsourcing datasets already do this for a small number of examples as attention checks. So we introduce a procedure that takes this existing test-retest data and uses it to estimate each annotator's primary label for an entire dataset. Very briefly, here's how that procedure works. First, we estimate p-flip, the probability that a given annotation will differ from an annotator's primary label, using test-retest data. Or if there isn't enough test-retest data, we use SVD to estimate p-flip. Then we resample a new test set from a label distribution, which we find by correcting the observed distribution using p-flip. And with our procedure, we find that when you consider annotator disagreement, that 0.95 ROC AUC classifier, which seems like it should be good enough for production, should actually be closer to a dramatically lower 0.73, which is really not. In fact, we find that no classifier could do better than 0.73. Even if we simulate a perfect Oracle classifier that cheats and always predicts aggregated labels straight from the test set, we can't do better. And we also find big corrections for other social computing tasks like misinformation and adult content detection. But for traditional ML tasks, like image classification, the corrections are far smaller. So to leave you with some parting thoughts. First, how might we design a product differently if we knew that the classifier's best possible performance was 0.73? And second, this work is just a start. We hope the HCI community will do more to help guide ML researchers' work with better metrics. Thank you.